Hello, my name is Felix, and this is a video about SpaceX's Falcon 9 grid fins. Grid fins are actuators that provide stability and control to a missile or rocket about its three axes: roll, pitch, and yaw. They feature a lattice of small aerodynamic surfaces arranged in a symmetrical grid pattern and positioned in an X formation around the top of Falcon 9's booster. They begin folded inwards as the Falcon 9 lifts off. It passes through the atmosphere up to 80 kilometers where the engine shuts off and the second stage separates from the booster. The booster rotates 180 degrees and the grid fins are deployed as it falls back into the atmosphere. As the booster descends and the atmospheric density increases, the booster hands over control from the gas thrusters to the grid fins, which are then able to guide it down extremely accurately to the landing pad. Grid fins, however, are not a new technology invented by SpaceX. They were first developed by Russian researchers in 1955, led by Professor Bolotsakovsky. Work done in this research became useful during the Cold War, and the grid fins were used on the Soviets' N-1 rockets and on their ballistic missiles. Since then, their applications include use on the US's Massive Ordnance Air Blast Bomb, the first private company orbital rocket from China, Hyperbola 1, and lastly, they are currently being developed for SpaceX's new Super Heavy rocket. Grid fins work by allowing air flowing through them to interact with the aerodynamic surfaces. When aligned with the free stream, the air simply passes through the grid fin and continues in the same direction. However, it is possible to see that as the grid fins are rotated by an angle, this diverts the air as it comes in contact with the inside of the aerodynamic surfaces. This then results in a force vector which acts perpendicular to the aerodynamic surface and produces a moment about the centre of mass of the vehicle, giving control authority in roll, pitch, and yaw. Due to the lattice structure, the grid fins have a large surface area with a very short chord length compared to planar aerodynamic surfaces, resulting in a very compact design. This allows for the grid fins to generate large forces whilst maintaining relatively small torque requirements for the actuator control mechanism. This reduces the size, mass, and complexity of the system, a big advantage for its use on the booster. In addition to this, the small grid fins are then able to be folded inwards for reduced drag on the booster's ascent. Grid fins were also chosen for use on the Falcon 9 due to their effectiveness across a large range of Mach numbers, from subsonic all the way up to hypersonic, but with an exception when going transonic. At subsonic flows, the air travels, as would be expected, through and out the other side of the grid fin. As it enters the transonic region, shock waves begin to develop on the aerodynamic surfaces, which grow into a large bow shock wave at the front of the grid fin. This effectively produces a pressure boundary and the air is diverted around the outside of the fin. At this point, the grid fin is completely ineffective as a control surface, acting as a flat plate. However, as the Mach number increases further, the shock cone becomes increasingly angled backwards to the point at which it passes through without interacting with the grid fin, allowing air to pass through again and becoming effective. Interestingly, the Falcon 9 Block 5 edition of the booster uses swept grid fins which provide better zero lift total drag and lift-to-drag ratio over unswept ones. SpaceX made the grid fins from aluminium in its first iterations due to it being cheap, lightweight, and easy to manufacture. The melting point of aluminium is approximately 600 degrees C, which is often exceeded on re-entry, and so they gave it an ablative white paint coat to prevent failure. They found that after use, significant maintenance and recoating was needed, which did not align with their aim of rapid reusability. Therefore, in the current design, they are made from titanium, which although is very hard to tool, it is extremely resistant to corrosion and has a high melting temperature of 1725 degrees C, which means it can be reused indefinitely with no maintenance. It is also stronger, which allowed SpaceX to remove some structural supports that were required in the aluminium version. Overall, the grid fins have performed exceptionally well for the Falcon 9, with only one grid fin failure out of 288 Falcon 9 missions.